What specific problem does the listening while speaking language model, LSLM, aim to solve in the context of interactive speech language models, ISLMs?
The listening while speaking language model, LSLM, aims to solve the problem of full duplex modeling, FDM, in interactive speech language models, ISLMs, which is crucial for enabling real-time natural communication. Traditional models are limited to turn-based conversations, failing to handle simultaneous listening and speaking, which is essential for effective turn-taking in dialogue. LSLM integrates both listening and speaking channels into a single end-to-end model, allowing it to process real-time audio input while generating speech. This capability addresses the challenges posed by noisy environments and the need for sensitivity to unseen speakers, ensuring that the model can recognize and respond to interruptions appropriately. By employing strategies like middle fusion for signal integration, LSLM enhances both speech generation and interactive capabilities, thereby improving user experience in conversational AI.
Can you provide a step-by-step illustration of how the proposed LSLM works, including the interaction between the listening and speaking channels?
The proposed listening while speaking language model, LSLM, operates through a structured interaction between its listening and speaking channels. First, the model utilizes a streaming self-supervised learning SSL encoder to process real-time audio input, generating continuous embeddings from the listening channel. Simultaneously, the speaking channel employs an autoregressive token-based text-to-speech (TTS) model to synthesize speech based on context and previously generated tokens. During the inference phase, both channels interact by feeding their respective outputs into the model. The speaking channel generates the next token while considering the context and the processed information from the listening channel. This integration allows the LSLM to detect interruptions in real time, enabling it to stop speaking and respond appropriately when an interruption token, IRQ, is detected, thus facilitating effective turn-taking in conversation.
Could you give a concrete example that demonstrates the functionality of LSLM in a real-time scenario, including how it handles interruptions?
A concrete example demonstrating the functionality of the listening while speaking language model, LSLM, in a real-time scenario is the voice-based full duplex modeling FDM setting. In this scenario, LSLM can be interrupted by various spoken commands from unseen speakers, such as when a user says "stop" while the model is generating speech. The LSLM is designed to detect this interruption and respond appropriately by stopping its speech output within a detection interval of 0.5 seconds after the interruption begins. Experimental results indicate that LSLM maintains high sensitivity to interruptions, achieving a precision of 87.69% and a recall of 82.77% in noisy conditions, showcasing its ability to distinguish between human voice commands and background noise. This capability allows LSLM to effectively engage in natural, real-time conversations, responding to user inputs without significant delays or misinterpretations.
What advantages does LSLM present over existing speech models in terms of real-time interaction and robustness to noise?
The listening while speaking language model, LSLM, presents significant advantages over existing speech models by enabling simultaneous listening and speaking, which enhances real-time interaction capabilities. Unlike traditional models that are limited to turn-based conversations, LSLM incorporates full duplex modeling, FDM, allowing it to detect turn-taking in real time and respond immediately to interruptions. Additionally, LSLM demonstrates robustness to noisy environments as it can effectively distinguish between human speech and various background noises, ensuring that it does not misinterpret interruptions as noise. Experimental results indicate that LSLM maintains high performance in both command-based and voice-based scenarios, even under challenging conditions with unseen speakers and background noise. This dual capability of real-time interaction and noise robustness positions LSLM as a more effective solution for realistic conversational AI applications compared to previous models.
How did you validate the effectiveness of LSLM in your experiments? Please detail the datasets, metrics, and criteria used for evaluation.
The effectiveness of the listening while speaking language model, LSLM, was validated through two primary settings: command-based FDM and voice-based FDM. For the command-based FDM, we utilized the Libre TTS dataset, which contains 585 hours of speech-text pairs, and tested it on Libre TTS test set B with 500 utterances, measuring the word error rate, WER, as the primary metric for TTS capability. In the voice-based FDM, we employed the speech commands dataset, which included a diverse set of interruption commands from unseen speakers, and evaluated the model's interactive capability using precision, recall, and F1 score metrics. Successful turn-taking was defined as the model stopping speaking within a 1-second interval after an interruption began, allowing us to construct a confusion matrix to assess performance. The experiments demonstrated that LSLM maintained competitive TTS capability while effectively handling real-time interruptions, particularly with the middle fusion approach, yielding the best results across both settings.
What limitations or potential drawbacks have you identified in the LSLM approach, specifically regarding its application in real-world scenarios?
The LSLM approach, while innovative, has notable limitations in real-world applications. Firstly, it struggles with noisy environments, as indicated by the performance drop in interactive capabilities when background noise is present, leading to misjudgments in turn-taking. Additionally, the model's ability to handle interruptions from unseen speakers is challenged, resulting in higher word error rates, WER, in voice-based FDM settings compared to command-based scenarios. The experiments revealed that the middle fusion method, although optimal, still faces difficulties in distinguishing between human voices and noise, which can hinder effective communication. Lastly, the reliance on specific keywords for command-based interactions limits its flexibility and adaptability in dynamic conversational contexts.